Here we have a supply system of 12 volt, 3 capacitors connected in serial. The first one is 0.10 farad, the next one 0.08 farad, and the last one is 0.05 farad, or 50 millifarad, 80 millifarad, and 100 millifarad. We also have a switch out here, so right now the system is disconnected, but when we connect the switch we will have a current in the serial connection and we will charge all the capacitors. We know basically that the charge of a capacitor is, for example, the current multiplied by time, or it is the voltage across the capacitor multiplied by the capacitance of the capacitor. Then we can calculate the charge. In a serial connection we know that the current must be the same and the time for all the capacitors are also the same. So the charge of all the capacitors must be the same. Right down here, Qs is equal to Q1, Q2 and Q3. And Qs, it is equivalent for all the capacitors. It means that we want to create the same circuit with only one capacitor. So that's the charge for the only capacitor if we want to simplify this circuit. And we can see here also that the charge is the voltage times the capacitance. So instead of the charge we can say voltage times capacitance. That was for the serial capacitor, and that's the supply voltage. And then the voltage for capacitor number 1 times the capacitance for capacitor number 1, and so for number 2 and number 3 as well. So we can see that you higher the capacitance, then the lower the voltage must be, because the charge is the same of all the capacitors. We also know in a serial connection that the supply voltage is equal to the sum of all the voltage across the components. And instead of the voltage we can write it must be the charge divided by the capacitance. So the charge divided by the capacitance for the serial connection must be equal to the charge divided by C1, charge by T2, and the charge divided by C3. And up here it is the same charge, because we write up here the charge must be the same for all the capacitors. Now we can say that the charge it can be 1, so we have that 1 divided by Cs, the equivalent, is 1 divided by C1 plus 1 divided by C2 plus 1 divided by C3, and so on if we got more than 3 capacitors. And this formula we can remember from the parallel resistors. That's the same system. So if we want to calculate the equivalent capacitor for all the 3, we have to use the formula. So we can find out. The first one is 0.1, next one is 0.08, and the last one is 0.05. These 3 numbers down here we have to add and then take the reciprocal, so plus plus and 1 divided by x. Then we can see here that's the value for the total capacitance for the equivalent, and it is 23.5 millifarad. We store that in number 1, and now here we can see we can calculate the charge for the serial capacitor, because now we have the value for Cs and the voltage across the equivalent capacitor must be the total supply voltage. So we just have to multiply by 12, and then we have the charge of all the capacitors is 282 millicoulomb. This charge we can again divide by the capacitance, then we have the voltage. So actually here the voltage across capacitor number 1 is the charge divided by the capacitance. So here's the charge, and then we can divide with the capacitance for number 1, 0.1 divide. Then the voltage across the first capacitor should be 2.82 volt. Then we can do the same for the next one. And finally, number 3. So now we can control the voltage across the capacitors. When we just switch on the system, we can see all the capacitors are charged, plus minus, and we can measure the voltage. The first one, 2.824, 2.824, right? Next one should be 3.529, 3.529, yes, and finally 5.647, 5.647, yes, that's correct. So that's the way to calculate capacitors which are connected in serial. It looks like resistors connected in parallel. And up here we have 2 basic formula to calculate the charge on a capacitor.